Tonight, we're going to explore one of the most extraordinary journeys in human history. Two spacecraft launched in 1977, with computers less powerful than a modern calculator. They were designed for a 5-year mission to study Jupiter and Saturn. Nearly 50 years later, they're still operational, billions of miles beyond their original destination. And when they reached the edge of the solar system, they discovered something that fundamentally changed everything we thought we knew. The boundary wasn't where scientists predicted. The structure was completely wrong. And the space beyond had properties that contradicted every model. 9 discoveries that proved we didn't even understand our own cosmic neighborhood. By the end of tonight, you're going to understand how two 1970s spacecraft revealed that the edge of our solar system is far stranger than anyone imagined. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The year is 1977. NASA launches 2 identical spacecraft. Voyager 2 lifts off on August 20th. Voyager 1 follows on September 5th, taking a faster trajectory. Each spacecraft weighs 1,820 pounds and stands 12 feet tall. The mission takes advantage of a rare planetary alignment that occurs once every 176 years. The original plan is simple. 5 years, Jupiter and Saturn, then drift silently as power fades. No one expects these spacecraft to last beyond their warranty. And absolutely no one anticipates that their greatest discoveries will come from what lies beyond the planets. Scientists in the 1970s believed they understood the edge of the solar system. The sun constantly emits a stream of charged particles called the solar wind. This wind flows outward at speeds around 250 to 500 miles per second. Eugene Parker, a physicist at the University of Chicago, predicted its existence in 1958. He showed that the sun's corona is so hot that gas can't be gravitationally bound and must flow outward continuously. Spacecraft measurements in the early 1960s confirmed his prediction. The solar wind flows every day, every year, constantly losing about 1 million tons of solar material per second. Eventually, this solar wind has to hit something. Between the stars, there's gas, about 0.1 atoms per cubic centimeter. Extremely thin, but over cosmic distances, even this tenuous gas has pressure and momentum. Our solar system orbits the galactic center at about 137 miles per second. From the sun's reference frame, the interstellar medium is a headwind. Where the solar wind meets this interstellar medium, a boundary forms. The heliopause, where the outward pressure of the solar wind equals the inward pressure of the interstellar medium. By the 1980s and 90s, scientists had built sophisticated computer models. They ran simulations that included magnetic fields, plasma dynamics, and the sun's motion. They predicted the heliopause would be roughly spherical, basically symmetric. A bubble surrounding the sun at a fairly consistent distance in all directions. They calculated it should be at about 90 to 100 astronomical units from the sun. 1 AU is roughly 93 million miles. So 90 to 100 AU meant about 8.4 to 9.3 billion miles. They knew the solar wind's strength from measurements near Earth. They estimated the interstellar medium's pressure from astronomical observations. They ran the equations. 90 to 100 AU, that's where Voyager should cross. Before reaching the heliopause, the solar wind would encounter the termination shock. This happens because the solar wind is supersonic, moving at 5 to 10 times the speed of sound in plasma. At the termination shock, the wind would suddenly slow from supersonic to subsonic. The plasma would heat up and compress. Models predicted the termination shock around 75 to 90 AU. Between the shock and the heliopause would be the heliosheath. Solar wind plasma that's been slowed and heated, flowing outward but also sideways. The heliosheath was expected to be perhaps 10 to 20 AU thick. Scientists were confident in the basic picture. The equations were well established. The physics had been studied for decades. They might be wrong about exact distances, but the overall structure should match. A termination shock around 75 to 90 AU. A heliosheath 10 to 20 AU thick. A heliopause around 90 to 100 AU. A clear boundary separating solar and interstellar space. They felt confident. But they were spectacularly wrong. Understanding these discoveries requires understanding the technology. Voyager accomplished everything with equipment from the early 1970s. The computers aboard each spacecraft have about 68 kilobytes of memory. Your smartphone has millions of times more. Yet, engineers can still upload software patches. In 2024, they debugged a memory chip failure after months of work, rewriting portions of 47-year-old code. Power comes from radioisotope thermoelectric generators containing plutonium-238. At launch, each generated about 470 watts. But plutonium decays. Power drops about 4 watts per year. By 2026, Voyager 1 has only about 249 watts remaining. Communication happens through the Deep Space Network. 3 massive antenna complexes in California, Spain, and Australia. Each antenna is 230 feet in diameter. The signal from Voyager 1 takes over 22 hours to reach Earth. A simple command exchange takes over 44 hours. The transmitter power is about 23 watts. By the time that signal reaches Earth, it's incredibly faint. This is the technology that discovered what lies at the edge. Voyager 1 reaches the termination shock on December 16, 2004. The spacecraft is at 94 AU, 8.7 billion miles from the Sun. Scientists had predicted the shock around 75 to 90 AU. Voyager is already beyond that range. The termination shock is where the solar wind suddenly slows from supersonic to subsonic speed. But the crossing isn't clean. Voyager detects the shock in 2002 at 85 AU. Then the shock moves. Over following months, the boundary shifts outward. Voyager finds itself back in supersonic solar wind. In 2003, Voyager detects it again. The shock washes over the spacecraft as it moves, then retreats. This breathing motion is caused by solar activity. Strong outbursts push the shock farther out. When activity drops, it moves inward. Voyager 2 crosses the termination shock on August 30th, 2007 at 84 AU. Wait. Voyager 2 crossed closer to the Sun than Voyager 1. About 10 AU closer, 930 million miles closer. If the boundary is spherical, both should cross at roughly the same distance. This is the first solid evidence that the shape is wrong. After crossing the termination shock, both Voyagers enter the heliosheath. Scientists expect slowed solar wind plasma flowing outward, turbulent but predictable. Instead, they discover something completely unexpected. In 2009, data analysis reveals the heliosheath isn't smooth. It's filled with magnetic bubbles, hundreds of them. Each bubble about 100 million miles across, wider than the distance from Earth to the Sun. The bubbles form when magnetic field lines disconnect and reconnect, creating isolated pockets of magnetic field. No model predicted this foam-like structure. Scientists had assumed tangled magnetic fields, but not discrete bubbles. The discovery changes understanding of how magnetic fields behave at the solar system's edge. It suggests magnetic reconnection happens far more frequently than anyone thought. These bubbles might also affect how galactic cosmic rays enter the solar system. Particles could get trapped in bubbles, bouncing around, or flow along bubble boundaries. The foam structure creates a complex maze for incoming particles. This is shocking discovery number one. The heliosheath is foamy, filled with magnetic bubbles billions of miles across. Nothing like the smooth transition zone scientists predicted. Starting in 2010, Voyager 1 begins detecting something unusual: increasing levels of galactic cosmic rays. These high-energy particles from supernova explosions should increase sharply at the heliopause, not in the middle of the heliosheath. Solar particles are decreasing when they should disappear suddenly. In June 2012, Voyager 1 detects something completely new: a region where magnetic field lines align directly, radially, pointing straight outward from the Sun. Not tangled, not twisted, perfectly organized. And particles are flowing along these field lines in both directions. Solar particles flowing outward, galactic cosmic rays flowing inward. The field lines are acting like a highway, connecting the heliosheath to interstellar space. Scientists call it the magnetic highway. No model predicted this. The leading theory is that the Sun's magnetic field is connecting to the galactic magnetic field. Where field lines merge, particles can flow freely both ways. Voyager 1 spends about 2 months in this magnetic highway. During this time, cosmic ray intensity is higher than anywhere else in the heliosheath. Solar particle intensity is lower. The spacecraft is sampling a region with direct access to interstellar space, even though it hasn't crossed the heliopause yet. This is shocking discovery number 2. The magnetic highway. An unexpected structure allowing particles to flow between the heliosheath and interstellar space. On August 25, 2012, everything changes for Voyager 1. Solar wind particles essentially vanish. Cosmic rays jump to a high, steady level. The change happens over a few days, but the magnetic field direction doesn't change. This causes confusion. Some scientists argue Voyager has crossed the heliopause. Others argue the lack of magnetic field rotation means it hasn't. The debate continues for over a year. Finally, in September 2013, NASA officially announces Voyager 1 crossed the heliopause on August 25, 2012. The spacecraft is at 121 AU, 11.2 billion miles from the Sun, far beyond where models predicted. Not 90 to 100 AU. 121 AU. About 26 AU farther than expected. 2.4 billion miles beyond the predicted boundary. Voyager 2 crosses on November 5, 2018 at 119 AU. Both crossed at roughly the same distance from the Sun. This reveals the heliosphere is somewhat symmetric at the equator, but compressed in the direction of the Sun's motion through the galaxy. The shape is more like a bullet or teardrop than a sphere. The Sun moves at about 137 miles per second relative to the local interstellar medium. From the Sun's reference frame, the interstellar medium is a headwind. This compresses the nose and stretches the tail. This is shocking discovery. Number 3. The heliopause distance was wrong by billions of miles, and the shape is asymmetric, compressed by the Sun's motion through the galaxy. In 1992, both Voyager spacecraft detected something strange: an excess of ultraviolet light from a specific direction beyond the heliopause. The light was coming from a region the spacecraft hadn't reached yet. Scientists suspected this might be neutral hydrogen piling up at the boundary. The Voyager ultraviolet spectrometers detected a glow at a wavelength called Lyman alpha. This is the characteristic wavelength emitted when hydrogen atoms absorb and re-emit ultraviolet light from the Sun. The glow was brighter than expected from hydrogen within the solar system alone. The excess suggested a source beyond the heliopause. But the data was inconclusive. The signal was at the edge of detection capabilities, and interpretations varied. Fast forward to 2018. NASA's New Horizons spacecraft, exploring the Kuiper Belt, detects the same ultraviolet glow. New Horizons carries the ALICE ultraviolet imaging spectrometer designed to study Pluto's atmosphere. After the Pluto flyby in 2015, the spacecraft continued outward into the Kuiper Belt. From there, billions of miles from Earth, it could observe the ultraviolet sky without interference from Earth's geocorona. Multiple measurements confirm the excess ultraviolet glow. The source is a region just beyond the heliopause. Scientists call it the hydrogen wall, a name that captures both its composition and its nature as a barrier. Here's what's happening in detail. Neutral hydrogen atoms from interstellar space flow toward the solar system. These atoms aren't charged, they're just hydrogen nuclei with their electrons still attached. They drift through the galaxy as part of the interstellar medium. When they reach the heliopause, they encounter the solar wind pushing outward. But neutral atoms aren't affected by magnetic fields or electric fields. They pass through the heliopause without being deflected. However, once inside the heliosphere, they encounter intense solar ultraviolet radiation. This radiation can ionize the atoms, stripping away their electrons. Once ionized, the atoms become charged, and the solar wind can push them. So neutral hydrogen flows inward, gets ionized, and is swept back outward by the solar wind. But right at the heliopause boundary, the process creates a traffic jam. Neutral atoms flowing inward encounter a region where ionization rate is extremely high. Many atoms get ionized and swept back before they can penetrate deep into the heliosphere. The result is a buildup of neutral hydrogen just beyond the heliopause. Like cars slowing down at a toll booth, creating congestion behind it. The hydrogen wall is estimated to be at about 200 to 400 AU from the Sun, far beyond where either Voyager has traveled. The exact location depends on properties of the interstellar medium and the solar wind. It's not a sharp boundary like a physical wall. It's a region where hydrogen density is significantly higher than the surrounding interstellar medium, perhaps 2 to 3 times higher concentrated in a zone tens of AU thick. The wall is heated by the collision between solar wind and interstellar medium. When solar wind particles finally lose their energy and momentum at the heliopause they've been traveling for billions of miles, they're still hot, still energetic. The interstellar medium particles, flowing inward, also carry kinetic energy. Where these two flows meet, they collide, they compress, they transfer energy. The result is heating. Temperatures in the hydrogen wall region reach 30,000 to 50,000 degrees Fahrenheit. That's 16,650 to 27,760 degrees Celsius. Hot enough to ionize atoms, creating a plasma sheath. At these temperatures, atoms move at tremendous speeds. The thermal velocity of hydrogen at 30,000 degrees is about 20 miles per second. Atoms are zipping around, colliding with each other, emitting radiation as electrons transition between energy levels. The region glows in ultraviolet light. This is what Voyager and New Horizons detected. Some researchers call it a wall of fire. The name is evocative and captures the high temperatures. Though fire implies combustion, and there's no oxygen out there, no chemical burning, it's more accurate to call it a superheated plasma barrier, a region where gas is so hot that atoms are stripped of electrons where matter exists in the fourth state, not solid liquid or gas, but plasma. This thermal wall is thicker, hotter, and more dynamic than models predicted. Early models suggested the hydrogen wall might be relatively cool, just a slight enhancement in density. The measurements show it's much more dramatic. The heating is significant. The density enhancement is substantial. The region is more structured. The Voyagers detected hints of it through ultraviolet observations decades ago. New Horizons confirmed it with more sensitive instruments and better observing geometry. But no spacecraft has reached it yet. The wall sits beyond where Voyager 1 and 2 currently are. They detected it remotely, not by crossing through it. Voyager 1 is at about 160 AU in 2026. Voyager 2 is at about 132 AU. The hydrogen wall is at 200 to 400 AU. Even traveling at 38,000 miles per hour, Voyager 1 won't reach it for another 40 to 120 years, long after the spacecraft have fallen silent. Understanding this hydrogen wall is crucial for multiple reasons. It may act as an additional shield protecting the inner solar system from galactic cosmic rays. Cosmic rays are charged particles, mostly protons, traveling at nearly the speed of light. When they encounter the hydrogen wall, they interact with the plasma there. Some get deflected by magnetic fields in the wall. Some lose energy through collisions with hydrogen atoms. The wall might filter out about 70% of lower energy cosmic rays. This is significant because cosmic rays affect Earth's atmosphere and climate. They ionize the atmosphere, creating pathways for lightning. They produce isotopes like carbon-14 and beryllium-10 used for dating ancient materials. They contribute to radiation dose for astronauts and airplane passengers. Over geological timescales, cosmic ray flux on Earth has varied. We see this in isotope records, preserved in ice cores and sediment layers. Some variation comes from Earth's magnetic field changes, some from nearby supernova explosions, creating bursts of cosmic rays. Some might come from heliosphere shielding changes as the Sun moves through regions of different interstellar pressure. If the Sun moves into a denser region of interstellar space, the heliopause might compress, moving closer to the Sun. The hydrogen wall properties would change. Cosmic ray shielding might increase or decrease. This could affect Earth's climate and radiation environment. The hydrogen wall also reveals how the solar system interacts with the galaxy on large scales. It's not a clean boundary where solar influence suddenly ends. It's a complex transition zone with multiple layers, each with different physical properties. Starting from the Sun outward, you have the solar wind flowing supersonically at 250 to 500 miles per second. At 75 to 90 AU, you hit the termination shock where the wind slows abruptly. From there, to 120 AU is the heliosheath filled with magnetic bubbles and turbulent plasma. At 120 AU is the heliopause, where solar wind particles finally stop and interstellar medium dominates. From 120 to 200 AU is a mixing region where solar and interstellar influences overlap. At 200 to 400 AU is the hydrogen wall, where neutral hydrogen accumulates and heats. Beyond that might be a bow shock in the interstellar medium, where the interstellar flow encounters the obstacle of the heliosphere. Models predict this bow shock at 140 to 230 AU, but measurements by New Horizons suggest it might not exist or might be much farther out. Each layer affects how particles and energy flow between the Sun and the galaxy. Each layer has its own magnetic field configuration, temperature, density, and dynamics. The hydrogen wall is a critical piece of this structure. It's where the final transformation happens, where the last vestiges of solar influence meet the true galactic environment. Future missions will need to cross through the hydrogen wall to fully understand it. The proposed interstellar probe, if it's built, might reach the wall in the late 21st century. Instruments on that spacecraft could measure the wall's properties directly. Temperature, density, composition, magnetic field structure. How thick is it exactly? How does temperature vary across it? What's the ionization fraction? How much neutral versus ionized hydrogen? Are there waves or instabilities in the plasma? How does it respond to solar activity changes? All questions that can only be answered by being there. The wall also has implications for any future interstellar mission. A spacecraft traveling to another star must eventually cross this barrier. The superheated plasma might affect the spacecraft's materials. At 30,000 to 50,000 degrees, the thermal radiation is intense. Though the plasma is so thin that heat transfer would be minimal. The main concern would be ionization of any atoms or molecules on the spacecraft's surface, creating a slight plasma sheath around the spacecraft. This could affect radio communications or cause electrostatic charging. Future mission planners need to account for this. The hydrogen wall is one more example of the universe being more complex than our models suggest. Scientists knew there would be hydrogen between the stars. They suspected some might accumulate near the heliopause. But the magnitude, the temperature, the structure, all exceed early predictions. Every time we measure something directly, we find reality is richer than theory anticipated. This is shocking discovery. Number 4. The hydrogen wall. a superheated barrier of accumulated hydrogen beyond the heliopause. A wall of fire protecting our solar system that scientists only recently confirmed exists. A structure that revealed the boundary between our solar system and the galaxy is more complex than anyone imagined. Voyager 1 is the first spacecraft to directly sample the interstellar medium. The density is about 0.08 particles per cubic centimeter. The temperature is about 54,000 to 90,000 degrees Fahrenheit. The pressure is extraordinarily low, but enough to balance the solar wind at the heliopause. Voyager detects plasma oscillations in the interstellar medium, waves of compression and rarefaction traveling through the plasma. In 2012 and 2013, Voyager 1 detects several bursts of oscillations. The frequency allows scientists to calculate electron density. Different measurements give slightly different values. The density isn't perfectly uniform. It varies by 10 to 20% over distances of a few AU. But here's what's truly surprising. The variations show structure, patterns, suggesting the interstellar medium has features, not just random fluctuations. In 2014 and beyond, continued measurements reveal the local interstellar medium contains clouds, regions of slightly higher or lower density, drifting past the solar system. The Sun is currently moving through a region called the local interstellar cloud. This cloud is a few light-years across. Density is slightly higher than the average interstellar medium, but the cloud has boundaries, structure. Voyager is detecting those structures as it moves through interstellar space. In thousands of years, the Sun will move out of this cloud into a different region. The interstellar pressure will change. The heliosphere will change shape and size. The termination shock and heliopause will move. Voyager is giving us a snapshot of conditions as they exist now, but those conditions aren't permanent. The galaxy is dynamic. Clouds drift, supernova shock waves propagate. The interstellar medium changes over time. This is shocking discovery number 5. The interstellar medium has structure, clouds with varying density drifting through our neighborhood. The space between stars isn't uniform, but filled with features we're only beginning to map. One of Voyager 1's most surprising findings involves cosmic rays. Scientists expected cosmic ray intensity to increase in interstellar space, and that part was correct. Voyager measures about 10 to 20% higher intensity beyond the heliopause. But the directional distribution is unexpected. Cosmic rays aren't coming uniformly. There's clear enhancement from certain directions, deficit from others. Voyager 1 detects lower cosmic ray intensity from the Galactic center direction. Counterintuitive. The Galactic center has the highest star density and most supernova explosions. You'd expect more cosmic rays from that direction. The explanation might be that the galactic magnetic field is stronger toward the center. Cosmic rays trying to propagate outward from the inner galaxy get trapped and scattered. Fewer reach our local region from that direction. But there's another anomaly. In 2020 and 2021, both Voyagers detect unusual spikes in cosmic ray intensity. Brief increases lasting weeks or months. These spikes don't correlate with known solar events. They might be caused by structures in the local interstellar medium, magnetic field variations that temporarily focus cosmic rays toward the spacecraft. Or they might be shock waves from distant stellar events. A supernova explosion light-years away could produce a shock wave that propagates through the interstellar medium for thousands of years. When it passes Voyager, cosmic ray intensity temporarily increases. Scientists are still analyzing these anomalies, trying to understand what causes them. This is shocking discovery number 6. Anomalous cosmic ray behavior, spikes and directional variations that reveal structure in the local interstellar environment. In 2012 and 2013, Voyager 1 detects what scientists call tsunami waves. Shock waves traveling through the interstellar medium caused by the Sun. When the Sun produces a powerful outburst, that pulse travels outward through the heliosphere. When it reaches the heliopause, it hits like a hammer. The impact launches a shock wave into the interstellar medium. These waves travel at the sound speed in interstellar plasma, about 60 miles per second. Voyager 1 detects the first tsunami in October and November 2012. The plasma wave instrument detects oscillations lasting several weeks. A second tsunami arrives in April and May 2013. A third in March 2014. Each wave traces back to a solar event years earlier. The Sun has a major outburst. The pulse travels outward at supersonic speed through the heliosphere, hits the heliopause, launches a shock wave into interstellar space. Months or years later, Voyager detects the wave passing over it. This reveals the Sun's influence extends far beyond the heliopause. Not as solar wind plasma, which is confined to the heliosphere, but as pressure waves propagating through the interstellar medium. These waves probably dissipate over tens of AU, but they're detectable billions of miles beyond the boundary. Other stars probably produce similar waves. A massive star with powerful stellar wind could create larger waves. An interstellar spacecraft might encounter shock waves from multiple stars. This is shocking discovery number 7. Tsunami waves from solar storms propagate through interstellar space billions of miles beyond the heliopause. The Sun's influence reaches farther than anyone imagined. Magnetic field measurements in interstellar space provided another surprise. Scientists expected the galactic field would be oriented differently from the Sun's field. Models predicted a rotation at the heliopause crossing. Voyager 1 detects no such change. The field direction, after crossing, is essentially the same as before. Eventually, scientists conclude the local galactic field happens to run roughly parallel to the Sun's field. Pure coincidence. Voyager 2's crossing shows a small rotation, about 20 degrees. This reveals the field direction varies over distances of about 100 AU. The interstellar field isn't uniform, it's structured, twisted, tangled. But here's the additional discovery. The magnetic field strength in interstellar space is about 50 nanotesla, about 1/1,000,000th the strength of Earth's surface field. But it varies. In 2019 and 2020, Voyager 2 detects fluctuations. The field strength oscillates by 10 to 20%. These variations occur over timescales of months. They might be caused by magnetic structures in the interstellar medium, flux ropes, current sheets, turbulent eddies. The galaxy's magnetic field isn't smooth and uniform. It has texture, features, dynamics. Understanding this field is crucial for cosmic ray propagation, for interstellar spacecraft navigation, for modeling how the heliosphere interacts with its environment. This is shocking discovery. Number 8. Magnetic field variations in interstellar space revealing dynamic, structured galactic fields. In November 2026, Voyager 1 will reach a historic milestone: 1 light day from Earth. The distance at which a signal traveling at light speed takes exactly 24 hours to reach the spacecraft. Currently, in March 2026, signals take about 22.5 hours. By November, that will reach 24 hours. 1 full day for a signal to travel from Earth to Voyager 1. Another full day for the response to come back, a 48-hour round trip. This milestone is more than symbolic. It represents the practical limit of real-time spacecraft control. When engineers send a command, they must wait 2 days for confirmation. If something goes wrong, they can't respond quickly. The spacecraft must be increasingly autonomous, able to diagnose and fix problems without waiting for instructions. 1 light day is about 16 billion miles, or 26 billion kilometers. Voyager 1 is currently traveling at about 38,000 miles per hour. At this speed, it gains about 3.6 AU per year, about 335 million miles per year. It will take another 40,000 years to travel 1 light year. The milestone also highlights how far Voyager has come. In 49 years, it has traveled from Earth orbit to 1 light day. It will take 73,000 years at current speed to reach Proxima Centauri at 4.24 light-years. The 1 light day milestone reveals the scale of interstellar space. Even traveling for half a century, Voyager has barely begun the journey between stars. This is shocking discovery number 9. The 1 light day milestone approaching in November 2026. A reminder of both how far we've sent our technology and how vast the distances truly are. So, how did we get here? How did 2 spacecraft, designed for a 5-year mission, end up making these discoveries? The journey begins with Jupiter. Voyager 1 reaches Jupiter in March 1979. Voyager 2 arrives in July 1979. The encounters revolutionize understanding of the solar system's largest planet. Jupiter's atmosphere shows far more complexity than expected. The Great Red Spot reveals intricate structure. Before Voyager, astronomers knew the Great Red Spot existed, a massive storm visible from Earth for centuries. But they didn't know what caused it or how deep it went. Voyager images show it's a high-pressure system, an anticyclone rotating counterclockwise. The storm rises about 5 miles above, surrounding clouds. The color comes from complex organic molecules produced when sunlight breaks down simpler compounds in the atmosphere. The atmosphere has dozens of smaller storms. White ovals and brown barges, each larger than most hurricanes on Earth. These storms interact with each other, sometimes merging, sometimes passing by in complex dances governed by Jupiter's powerful winds and rotation. Lightning flashes in the atmosphere, similar to Earth's lightning, but enormous. Some bolts release 1,000 times more energy than typical lightning on Earth. Aurora blaze at both poles, similar to Earth's northern and southern lights, but vastly more powerful. Earth's aurora are caused by charged particles from the solar wind colliding with atmospheric molecules. Jupiter's aurora are powered by its rotation and magnetic field. As Jupiter's magnetic field sweeps through space, it picks up charged particles from Io's volcanism. These particles spiral along field lines toward the poles, slamming into Jupiter's upper atmosphere at tremendous speeds. The result is aurora 1,000 times brighter than Earth's, stretched for thousands of miles across polar regions. Cloud bands show winds exceeding 400 miles per hour. Earth's jet streams reach maybe 200 miles per hour at most. Jupiter's winds are driven by the planet's rapid rotation. Jupiter completes one rotation in just under 10 hours. Despite being 11 times wider than Earth, it spins in less than half the time. This creates powerful Coriolis forces that organize the atmosphere into alternating bands of east-flowing and west-flowing winds. But the biggest surprises come from Jupiter's moons. Astronomers had known about Jupiter's 4 large moons since Galileo discovered them in 1610. Io, Europa, Ganymede, and Callisto, collectively called the Galilean moons. From Earth, they appeared as tiny points of light. No telescope could resolve surface features. Astronomers could measure their sizes, orbits, and brightnesses, but little else. Voyager changed that. Io, the innermost large moon, was expected to be cold and dead, like Earth's moon. Linda Morabito, a navigation engineer, was examining images to determine Voyager 1's precise position. She noticed a strange umbrella-shaped plume extending from Io's limb, a volcanic eruption, the first active volcano ever discovered beyond Earth. This discovery was revolutionary. For decades, scientists had assumed the solar system's smaller bodies were geologically dead. Only Earth had active volcanism, or so they thought. Io shattered that assumption. It turns out to be the most volcanically active body in the entire solar system. Voyager discovers 9 active volcanoes during the flybys. Later, observations catalogue over 400 volcanic centers. The surface is constantly resurfaced by sulfur and silicate lava, giving Io its distinctive yellow, orange, and red colors. Some volcanic plumes reach heights of nearly 200 miles above the surface. Material ejected at speeds exceeding 1,000 miles per hour. The volcanic activity comes from tidal heating. Jupiter's enormous gravity, combined with gravitational tugs from Europa and Ganymede, constantly flexes Io's interior. As Io orbits Jupiter, it experiences varying gravitational pull. When it's closer to Jupiter, the pull is stronger. When it's farther away, the pull is weaker. And Europa and Ganymede tug on Io as well, preventing its orbit from becoming perfectly circular. This constant flexing generates friction deep inside Io. Friction generates heat. Heat melts rock. Molten rock erupts as volcanoes. The process is called tidal heating. It was theorized before Voyager, but never confirmed. The discovery changed how scientists think about energy sources for geology. Not just radioactive decay in planetary interiors, but tidal heating from gravitational interactions can power volcanism and tectonics. This applies to Io, to Europa, to Saturn's moon Enceladus, and potentially to exomoons orbiting giant exoplanets in other star systems. Europa presents a different mystery. Its surface is smooth ice, crisscrossed with cracks and ridges. Very few craters, suggesting a young surface constantly renewed. The ice appears to be fractured and refrozen in complex patterns. Long linear cracks called lineae stretch for hundreds of miles. Some regions show chaotic terrain where the ice appears to have broken apart and reformed. Other areas have ridges, double ridges, running parallel. The implication is profound. Beneath that ice might be liquid water. An ocean kept liquid by tidal heating, though less intense than Io's. The same gravitational interactions that tear Io apart might be gently warming Europa's interior, enough to keep water liquid beneath the ice shell. Voyager can't prove the ocean exists. The evidence is circumstantial, based on surface features and theoretical models. But the possibility that Europa might harbor a subsurface ocean makes it one of the most intriguing targets for searching for life beyond Earth. Later missions, particularly Galileo, in the 1990s and 2000s, provide stronger evidence for the ocean. Magnetic field measurements suggesting a conducting layer beneath the surface. Surface composition showing salts that might come from an ocean below. But Voyager provided the first hints, the first suggestion that an icy moon might hide an ocean. Ganymede, the largest moon in the solar system, shows a complex surface. Old, dark terrain covered with craters from billions of years of impacts. Younger, brighter terrain with grooves and ridges. The moon appears to have undergone geological resurfacing at some point in its history. Perhaps from internal heating, perhaps from tidal forces. The mechanisms aren't fully understood. Callisto, the outermost Galilean moon, is heavily cratered. Its surface is ancient, perhaps unchanged for billions of years. A stark contrast to Io's constantly renewing surface and Europa's relatively young ice. Callisto shows what happens when a world doesn't have internal heat sources or tidal heating. It freezes geologically, its surface becoming a record of ancient impacts. Voyager also discovers Jupiter has rings. Faint, made of dust-sized particles, nothing like Saturn's spectacular ice rings. Astronomers had suspected rings might exist, but had never detected them from Earth. The rings are too faint, too thin to see with ground-based telescopes. Voyager 1 confirms their existence in 1979. The rings are thin and faint, composed of dust kicked up from small moons by micrometeorite impacts. The discovery suggests ring systems might be common around giant planets. Perhaps all giant planets have rings, some spectacular like Saturn's, others faint like Jupiter's. By the time Voyagers leave Jupiter, they've returned more data than all previous observations combined. Thousands of images showing details never seen before. Measurements of magnetic fields revealing Jupiter's enormous magnetosphere. Radiation environment data showing intense belts of trapped particles. Atmospheric composition measurements. Data on 4 major moons and several smaller ones. Discovery of a ring system. The mission is a spectacular success, exceeding every expectation. And Saturn is next. Voyager 1 reaches Saturn in November 1980. Voyager 2 arrives in August 1981. Saturn's rings had been observed since Galileo first saw them in 1610, though he didn't understand what he was seeing. He thought Saturn had ears or handles attached to it. It wasn't until the 1650s that Christian Huygens realized Saturn was surrounded by a ring. By the 1980s, astronomers knew Saturn had multiple rings separated by gaps. The A ring, B ring, C ring, the Cassini division, a large gap between the A and B rings. But they had no idea of the true complexity waiting to be discovered. Voyagers reveal each visible ring is actually thousands of individual ringlets. Complex structure on scales that couldn't be resolved from Earth. The rings aren't solid or continuous. They're made of billions of individual particles, ranging in size from dust grains to house-sized boulders. Each particle orbits Saturn independently, following the laws of orbital mechanics. The particles are mostly water ice, with some rocky material mixed in. The ice reflects sunlight brilliantly, making Saturn's rings the most spectacular in the solar system. The rings show waves, braids, kinks, and spokes. Dark radial features that rotate with the rings, visible in Voyager images. The mechanism for the spokes wasn't immediately understood. Later analysis suggested they're caused by electrostatic levitation of dust particles above the ring plane. Shepherd moons, tiny satellites orbiting near ring edges, whose gravity herds ring particles and maintains sharp boundaries. Prometheus and Pandora, two small moons flanking the F ring, keep that ring confined through their gravitational influence. As the moons orbit, their gravity tugs on nearby ring particles. Particles that drift too far inward are pulled back by one moon. Particles that drift too far outward are pulled back by the other moon. The result is a narrow ring with sharp edges, shepherded by the two moons. The F ring shows braided structure, unlike anything seen elsewhere. 3 or 4 strands that appear to wind around each other. Later observations show the braids change over time as the shepherd moons perturb the ring particles. The level of complexity is astonishing. Saturn's rings aren't just bands of debris orbiting the planet. They're a dynamic system where gravity, orbital mechanics, and particle collisions create structure on every scale. From features spanning thousands of miles down to individual particles a few feet across. Density waves propagate through the rings, similar to sound waves but caused by gravitational resonances with Saturn's moons, where particles orbit at specific ratios to a moon's orbit. The repeated gravitational tugs create waves. These waves compress and rarefy the ring material, creating spiral patterns visible in high-resolution images. Bending waves also appear, causing the ring plane to warp vertically in response to gravitational perturbations. The rings are thin, incredibly thin. Thousands of miles across, but only about 30 feet thick in most places. Thinner than a sheet of paper if you scaled Saturn down to the size of a beach ball. This thinness is maintained by particle collisions. Any particle with vertical motion eventually collides with other particles. The collisions damp out vertical motion, flattening the ring into a thin disk. Titan, Saturn's largest moon, was known to have an atmosphere. The only moon in the solar system with a thick atmosphere comparable to a planet's. This had been known since the 1940s, when Gerard Kuiper detected methane absorption in Titan's spectrum. But the true nature of Titan's atmosphere remained mysterious. Voyager 1 makes a close flyby, passing within 2,500 miles. The spacecraft sacrifices visiting other targets to make this close approach. The trajectory that allows a close Titan flyby prevents Voyager 1 from continuing to Uranus and Neptune. That's why Voyager 2 takes over for the ice giants. But the Titan encounter is worth the sacrifice. The atmosphere turns out even thicker than expected. Surface pressure, about 1.5 times Earth's at sea level. That's higher pressure than on any other moon or planet except Venus. Composition primarily nitrogen, like Earth's atmosphere. About 95% nitrogen, making it the only place besides Earth with a nitrogen-dominated atmosphere. The remaining 5% is methane and other organic compounds. Methane, ethane, propane, acetylene, complex organic chemistry happening in the atmosphere. The surface is hidden beneath opaque orange haze. Layers of photochemical smog created when sunlight breaks down methane in the upper atmosphere. The ultraviolet light from the sun splits methane molecules. The fragments recombine into more complex molecules, forming aerosol particles. These particles drift down through the atmosphere, creating the opaque haze that hides the surface. The smog particles are tholins, complex organic molecules similar to the compounds that might have existed on early Earth. Voyager can't see through to photograph the surface. The cameras see only the top of the haze layer, a featureless orange ball. But atmospheric data is fascinating. Temperature, pressure, composition measurements at different altitudes reveal a complex atmosphere with layers. A cold tropopause, where temperature reaches a minimum. A warmer stratosphere above. Vertical structure similar to Earth's atmosphere in some ways, but with methane playing the role water plays on Earth. Titan has a methane cycle analogous to Earth's water cycle. Methane evaporates from the surface, rises into the atmosphere, forms clouds, condenses, rains back down. The surface likely has lakes or seas of liquid methane and ethane, rivers and streams flowing with liquid hydrocarbons. Organic chemistry, driven by sunlight, breaking down methane and creating complex molecules. The temperature at the surface is about -290 degrees Fahrenheit, -179 degrees Celsius. Cold enough that water ice is rock hard, forming Titan's bedrock, but warm enough that methane can exist as a liquid, forming lakes and seas. Titan becomes another high-priority target for future exploration. The Cassini mission would later orbit Saturn for 13 years, from 2004 to 2017. The Huygens probe would land on Titan in 2005, returning the first images from the surface, revealing a world with methane lakes, river channels carved by liquid methane, and dunes made of organic sand. But that was decades in the future. For now, in 1980 and 81, Voyager has revealed Titan is a world of extraordinary complexity. A moon with weather, with seasons, with a surface shaped by erosion and deposition. The only place, besides Earth, where liquids flow on the surface, though on Titan those liquids are methane and ethane, not water. After Saturn, the two Voyagers diverge. Voyager 1 is sent on a trajectory above the solar system plane, heading into interstellar space as quickly as possible. It will visit no more planets. Voyager 2 continues to Uranus and Neptune, the only spacecraft to visit these distant ice giants, and it remains so to this day. Uranus, in January 1986. Uranus is odd from the start. Its axis is tilted 98 degrees relative to its orbital plane. It essentially rolls along its orbit like a barrel, rather than spinning like a top. This means the poles alternately point toward and away from the Sun during its 84-year orbit. Each pole experiences 42 years of continuous daylight, followed by 42 years of darkness. No one knows why Uranus is tilted this way. The leading theory is that early in the solar system's history, Uranus was hit by a massive object, perhaps an Earth-sized protoplanet. The impact knocked Uranus onto its side. Voyager 2 reveals Uranus's atmosphere as surprisingly bland. Few visible cloud features, unlike Jupiter's dynamic storms or Saturn's subtle banding. Pale blue color from methane in the upper atmosphere, absorbing red light. But beneath the bland appearance, winds reaching 560 miles per hour circle the planet. The spacecraft discovers 10 previously unknown moons, small irregular bodies orbiting in the outer reaches of Uranus's system. 2 new rings, adding to the 9 already known from ground-based observations. Uranus's rings are thin and dark, composed of dark particles, very different from Saturn's bright ice rings. The spacecraft also measures Uranus's magnetic field, finding it surprisingly tilted. The magnetic axis is tilted about 60 degrees from the rotation axis. On Earth, the magnetic and rotation axes are roughly aligned, tilted only about 11 degrees from each other. On Uranus, they're wildly misaligned. The magnetic field also doesn't pass through the planet's center. It's offset by about 1/3 of Uranus's radius. These oddities suggest something unusual about Uranus's interior structure. Perhaps the magnetic field is generated in a thin shell of electrically conducting fluid, rather than in a deep core like Earth's. But the most interesting discoveries come from Miranda, Uranus's 5th largest moon. Miranda is only 300 miles across, tiny by planetary standards. But it shows bizarre geology that shouldn't exist on such a small world. The surface is a patchwork of different terrain types. Regions of ancient, heavily cratered terrain, right next to regions of grooved terrain with parallel ridges and valleys. Enormous cliffs, including Verona Rupes, estimated at 6 miles high. Over 3 times the height of Valles Marineris walls on Mars. The tallest cliff in the solar system relative to the body's size. The surface looks shattered and reassembled, like a jigsaw puzzle put back together incorrectly. One theory suggests Miranda was broken apart by a massive impact. Then, the fragments reassembled under mutual gravity. Different terrain types jumbled together as pieces came back together in random orientations. Another theory invokes tidal heating. Perhaps Miranda's orbit was different in the past, more elliptical, causing tidal flexing and internal heating. This heat could have driven geological activity, creating the grooved terrain. Then the orbit became more circular. Heating stopped, and activity ceased. The cause remains uncertain, but Miranda definitely experienced something unusual. For such a small moon to show such dramatic geology is remarkable. Neptune, in August 1989, the farthest planet from the Sun, nearly 3 billion miles from Earth. Voyager 2's flyby is the culmination of the Grand Tour. 12 years after launch, the spacecraft has successfully visited all 4 outer giants. Neptune was expected to be similar to Uranus, another bland ice giant with little weather. Instead, Neptune shows the most dynamic atmosphere of any planet Voyager visited. The Great Dark Spot, an Earth-sized storm similar to Jupiter's Great Red Spot, a massive anticyclonic storm in Neptune's southern hemisphere. The Scooter, a bright cloud feature that circles the planet every 16 hours. Winds exceeding 1,300 miles per hour, the fastest winds measured on any planet in the solar system. Neptune's atmosphere is more active than Uranus's, despite being farther from the Sun and receiving less solar energy. The activity must come from internal heat. Neptune radiates about 2.6 times more energy than it receives from the Sun. This internal heat drives powerful convection in the atmosphere, creating the dynamic weather. Where this heat comes from isn't entirely clear. Perhaps residual heat from Neptune's formation 4.6 billion years ago. Perhaps ongoing gravitational settling of heavier elements toward the core. Either way, the heat makes Neptune's atmosphere far more dynamic than Uranus's. Voyager 2 discovers 6 new moons, small irregular bodies orbiting Neptune. 4 new rings, thin and faint like Uranus's rings. But the biggest surprise comes from Triton, Neptune's largest moon. Triton is unusual from the start. It orbits Neptune in the wrong direction, retrograde orbit opposite to Neptune's rotation. Extremely unusual for a large moon. All the major moons of Jupiter, Saturn, and Uranus orbit in the same direction their planet rotates. They formed from the same disk of material that formed the planet. But Triton orbits backward. The implication is clear. Triton wasn't formed alongside Neptune. It was captured, probably from the Kuiper Belt. Triton was once an independent object, perhaps similar to Pluto. At some point, it passed too close to Neptune. Neptune's gravity captured it into orbit. The capture process would have been violent, heating Triton's interior through tidal flexing. Over time, the orbit became more circular, but the retrograde direction remained. Triton shows active geology, despite being one of the coldest surfaces in the solar system. Surface temperature is -391 degrees Fahrenheit, -235 degrees Celsius. Yet, Voyager images show dark streaks on Triton's surface. Nitrogen ice geysers erupting from below the surface. The mechanism is thought to be seasonal heating. Even at Triton's distance from the Sun, sunlight can penetrate translucent nitrogen ice on the surface. Dark material beneath the ice absorbs sunlight and warms up slightly. The warming is tiny, just a few degrees, but enough to sublimate nitrogen ice. Nitrogen turns directly from solid to gas, building pressure beneath the surface. Eventually, pressure ruptures the surface. Nitrogen gas vents into space, carrying dark particles with it. The gas disperses, but the dark particles fall back to the surface, creating the dark streaks visible in Voyager images. Active geology on a world colder than any other solid surface measured in the solar system. With Neptune and Triton, Voyager 2's planetary mission ends. Both spacecraft have far exceeded original parameters. They discovered active volcanism on Io, the first beyond Earth. Hints of subsurface oceans on Europa, making it a target in the search for life. Jupiter's ring system, faint but present. Thousands of ringlets in Saturn's rings, revealing astonishing complexity. Titan's thick nitrogen atmosphere and methane cycle. 10 new moons at Uranus and 2 new rings. Miranda's bizarre fractured geology. Neptune's dynamic atmosphere with the fastest winds in the solar system. 6 new moons at Neptune and 4 new rings. Triton's nitrogen geysers on the coldest active surface known. Tens of thousands of images showing details never seen before. Measurements transforming our understanding of the outer solar system. And both spacecraft are still functional, still transmitting data, still capable of science. So NASA makes a decision. The Voyager interstellar mission begins. The spacecraft will continue outward, seeking the boundary where the sun's influence ends. Scientists have models and predictions about that boundary. All of them will turn out to be wrong in important ways. The Voyager discoveries have profound implications for any future attempt at interstellar travel. They've given us first direct measurements of the environment any interstellar spacecraft would traverse. And the reality is sobering. Voyager 1 has traveled for nearly 50 years and covered about 160 AU, 14.9 billion miles. Sounds impressive until you realize the nearest star, Proxima Centauri, is 4.24 light-years away. About 268,000 AU, about 25 trillion miles. At Voyager's speed of 38,000 miles per hour, it would take about 73,000 years to reach Proxima Centauri. 73,000 years. Longer than all of recorded human history, longer than humans have practiced agriculture, longer than the time since the last ice age ended. And Voyager isn't even heading toward Proxima Centauri. It's headed in a completely different direction. To make interstellar travel feasible, you need dramatically higher velocities. At least 10% of light speed for reasonable travel times to nearby stars. 10% of light speed is about 67 million miles per hour, about 1,700 times faster than Voyager. At that speed, Proxima Centauri would be about 42 years away. Still a lifetime, but within the span of a human career. You could send a spacecraft at age 25 and possibly be alive at age 67 when the first data arrives back. Though the signal would take another 4.24 years to return to Earth, so 46 years. Round trip, from launch to first contact with data. But reaching 10% of light speed requires enormous energy. The kinetic energy of a spacecraft is 1/2 times mass times velocity squared. That squared term means doubling velocity requires 4 times the energy. Reaching 10% of light speed requires about 3,000 times more energy per kilogram than Voyager's velocity. For a spacecraft, the mass of Voyager, about 1,800 pounds or 820 kilograms, the energy required would be about 9 times 10 to the 15th joules. That's roughly the energy in 220,000 tons of TNT, equivalent to a large nuclear weapon. And that's just the kinetic energy the spacecraft needs. The propulsion system has to provide that energy, which means burning fuel. But any fuel you carry adds mass, which requires more energy to accelerate, which requires more fuel. It's called the tyranny of the rocket equation. Current chemical rockets can't even come close. Nuclear propulsion, solar sails, ion drives, fusion rockets, all have been proposed, but none have been demonstrated at anything close to the required scale. And Voyager discoveries reveal additional challenges any high-speed interstellar craft would face. The interstellar medium contains about 0.08 atoms per cubic centimeter, mostly hydrogen and helium. At Voyager's speed, this doesn't matter much. The spacecraft occasionally hits a hydrogen atom. The impact has negligible effect. But at 10% of light speed, every collision becomes significant. The kinetic energy of impact is proportional to velocity squared. A collision at 10% of light speed has about 28 million times more energy than the same collision at Voyager's speed. A hydrogen atom hitting a spacecraft at 10% of light speed delivers about 6 electron volts of energy. That doesn't sound like much on its own. A single atom with 6 electron volts does essentially nothing. But there are a lot of atoms out there. A spacecraft with a 1 square meter cross-section traveling at 10% of light speed through the interstellar medium would encounter about 10 to the 14th hydrogen atoms per second. 100 trillion atoms per second, every single second, for years. Each collision delivers tiny energy, but they add up. The total power deposited by atomic impacts would be several thousand watts, continuous heating on the leading edge of the spacecraft for the entire journey. This energy appears as heat in the spacecraft's hull, requiring cooling systems or heat-resistant materials to survive. It also appears as radiation damage. Each high-speed impact can knock atoms out of the hull material, creating defects in the crystal structure. Sputtering, where surface atoms are ejected by the impact. Over years of travel through the interstellar medium, this erosion would be significant. Materials would become pitted and weakened. Structural integrity could be compromised. Electronics near the surface could be damaged by the cascade of secondary particles from each impact. And that's just from neutral hydrogen atoms. The interstellar medium also contains charged particles, cosmic rays. Voyager measured cosmic ray intensity in interstellar space at about twice the level in the inner solar system, about 10 to 20% higher than in the outer heliosheath. This confirms the heliosphere provides shielding, even billions of miles from the Sun. Cosmic rays are high-energy particles, with energies from millions to billions of electron volts. Some reach energies beyond what the Large Hadron Collider, the most powerful particle accelerator on Earth, can achieve. A single cosmic ray with 1 billion electron volts carries about 1/6 millionth of a joule. Not much energy, but that energy is concentrated in a single atomic nucleus. When it hits matter, it can penetrate deep, creating cascades of secondary particles as it collides with atoms. Each collision can displace atoms, break chemical bonds, damage DNA if it hits biological tissue. Over decades of travel through interstellar space, cosmic ray exposure would accumulate. Humans aboard an interstellar spacecraft would need heavy shielding, several feet of water, aluminum, or specialized materials, adding significant mass to the spacecraft. Electronics would need to be radiation-hardened, able to tolerate the accumulated damage, or use redundancy with backup systems that can take over when primary systems fail. Biological samples would need protection from accumulated radiation damage. Seeds, frozen embryos, or any other biological cargo would degrade over decades of exposure unless carefully shielded. Voyager's cosmic ray measurements give us the baseline radiation environment. Now, we know what to design for. Future missions can use this data to calculate required shielding thickness and mass. The magnetic field measurements also matter for interstellar mission design. Charged particle trajectories are affected by magnetic fields. Particles spiral along field lines as they travel. The galactic magnetic field is weak, only about 50 nanotesla, about 1/1,000,000th the strength of Earth's surface field. But over the vast distances of interstellar travel, even weak fields can deflect particles significantly. A charged particle, traveling for years through a 50 nanotesla field, will curve. The amount of curvature depends on the particle's energy and charge. For a spacecraft, using a magnetic sail, a proposed propulsion concept that uses magnetic fields to interact with the interstellar medium, knowing the field's strength and direction is crucial for navigation and trajectory planning. The spacecraft would deploy a large magnetic field, perhaps tens or hundreds of miles across. Charged particles in the interstellar medium would interact with this field, transferring momentum. Like a solar sail uses photons from the sun, a magnetic sail would use charged particles from the interstellar medium. But this only works if the field strength and particle density are adequate. Voyager's measurements provide the data needed to evaluate whether magnetic sails are feasible. The hydrogen wall presents another challenge. Any spacecraft leaving the solar system must eventually cross this barrier of superheated plasma. The wall sits at about 200 to 400 AU from the Sun, far beyond where the Voyagers currently are. Temperatures reach 30,000 to 50,000 degrees Fahrenheit, hot enough to ionize atoms and create plasma. A spacecraft crossing through this region would experience intense heating. The plasma might interact with the spacecraft's materials, causing erosion or chemical changes. Understanding the wall's properties is crucial for designing appropriate shielding and choosing materials that can withstand the environment. The Oort cloud presents yet another obstacle that Voyager's trajectory illuminates. The Oort cloud is a hypothetical shell of icy objects surrounding the solar system, thought to extend from about 2,000 AU out to as far as 100,000 AU. That's halfway to Proxima Centauri. Voyager 1 won't reach the inner edge for about 300 years at its current speed, won't exit the outer edge for about 30,000 years. An interstellar mission traveling 10 times faster would still spend 3,000 years crossing the Oort cloud. The spacecraft would be in interstellar space, as Voyager defines it, beyond the heliopause, but still within the Sun's gravitational sphere of influence, still technically orbiting the Sun, though in an extremely distant orbit. We don't know what conditions are like in the Oort cloud. No spacecraft has been there. No telescope can resolve individual Oort cloud objects. We infer its existence from the orbits of long-period comets that occasionally fall into the inner solar system. Is the density of objects high enough to pose collision risk? Are there dust grains that could damage a high-speed spacecraft? How much debris is left over from the solar system's formation out there? Voyager won't answer these questions because its instruments will be dead for thousands of years before it reaches the Oort cloud. But the fact that Voyager has traveled for 50 years and hasn't even reached the Oort cloud gives perspective on the challenge. The solar system is bigger than we thought. The journey to truly interstellar space, beyond all solar influence, is longer than we imagined. All these realities make interstellar travel look extremely challenging. Not impossible, but requiring technologies and capabilities far beyond what we currently possess. Advanced propulsion, reaching significant fractions of light speed. Robust materials withstanding decades of impacts and radiation. Power sources functioning for decades without maintenance. Communication systems, sending signals across light years. Autonomous navigation, because round-trip communication times make real-time control impossible. The Voyagers have shown us what we're up against. They've measured the environment we'd have to cross. They've revealed even our local cosmic neighborhood is more complex than we thought. This doesn't mean we shouldn't attempt interstellar travel. It means we need to be realistic about challenges and timescales. Perhaps the Voyager's greatest contribution to future interstellar exploration is showing it's possible to send something beyond the solar system and have it keep working. The engineering that went into these spacecraft, the redundancy, the simplicity, the robustness, has enabled them to function far longer than anyone expected. Future interstellar missions will need similar robustness, but magnified. If Voyager can last 50 years, an interstellar mission might need to last 100 years or more. If Voyager can communicate from 15 billion miles, an interstellar mission needs to communicate from 1 trillion miles or more. The challenges are immense, but the Voyagers proved we can build things that work in the interstellar environment, at least for decades. They're our proof of concept that leaving the solar system is possible. On February 14, 1990, Voyager 1 turned its camera backward for one last look at the solar system. The spacecraft was about 3.7 billion miles from Earth, about 40 AU beyond Neptune's orbit, heading outward toward the heliopause, still decades away at that point. NASA commanded Voyager 1 to rotate its scan platform and take a series of images, a family portrait of the solar system. Images of 6 planets: Earth, Venus, Jupiter, Saturn, Uranus, and Neptune. Mercury was too close to the Sun, lost in glare. Mars was too small and dim. Pluto was too faint to detect. In one of those images, Earth appears as a tiny dot, a pale blue dot, less than a pixel in size, suspended in a beam of scattered sunlight. Carl Sagan, who had been a driving force behind including cameras on Voyager and who worked on the Golden Record, saw that image and was moved to write one of the most profound reflections on humanity's place in the cosmos. He pointed out that everyone who had ever lived on that dot. Every human drama, every war, every romance, every triumph and tragedy, all of it played out on a mote of dust floating in a sunbeam. From Voyager's vantage point, Earth had no special significance. Just one planet among several, smaller than Jupiter, fainter than Venus, indistinguishable except that we know it's there because we came from it. The pale blue dot image connects to Voyager's discoveries at the edge in a profound way. The spacecraft that took that image went on to cross the heliopause, entered interstellar space, measured the galaxy beyond the Sun's influence. And from out there, from true interstellar space, Earth is even less significant. The entire solar system is a tiny bubble in the vastness of the galaxy. The Sun is one star among hundreds of billions. The heliosphere is one small region in the incomprehensible expanse of interstellar space. The discoveries the Voyagers made revealed that even our local cosmic neighborhood is more complex than we realized. If we're still learning about the boundary between solar system and interstellar space, how much more is there to learn about the galaxy, about the universe? The pale blue dot image is a reminder of scale, of how small we are, of how recent our presence is on cosmic timescales. Earth is 4.5 billion years old. Humans have existed for maybe 300,000 years. Civilization for maybe 10,000 years. Space exploration for less than 70 years. The Voyagers launched 49 years ago. They've been traveling for a human lifetime, and they've barely left the solar system. They're in the beginning of interstellar space, just beyond the heliopause. The nearest star, Proxima Centauri, is 4.24 light-years away. At Voyager's speed, about 73,000 years to get there. The spacecraft aren't headed toward Proxima Centauri. They'll pass nearest to other stars in about 40,000 years at distances over a light-year. True interstellar travel, traveling between stars, visiting other planetary systems, remains far beyond our capability. The Voyagers are interstellar in the sense they've left the heliosphere. They're in the space between stars, but they're not traveling to other stars. They're just drifting. And yet, what they've accomplished is extraordinary. 2 spacecraft, built with 1970s technology, have traveled farther than anything humans have ever made. They've visited worlds no one had ever seen up close. They've crossed a boundary no spacecraft had ever reached. They've measured conditions that had only been theoretical. They've shown us the universe is always more complex than our models suggest, that there are always surprises waiting, that exploration reveals things we didn't know. The pale blue dot image captures that spirit of exploration. Looking back at where we came from, seeing it with new eyes, recognizing both how precious it is and how small it is. And then turning around and continuing the journey outward into the unknown. By 2026, both Voyagers are still operational. This is extraordinary. They've lasted 10 times longer than their design lifetime, but they're dying. The plutonium in their RTGs decays. Power output drops steadily. Voyager 1 has about 249 watts remaining. Instruments are being shut down one by one to conserve energy. In 2020, NASA shut down the heater for Voyager 2's cosmic ray instrument. The instrument dropped to minus 74 degrees Fahrenheit. Engineers expected it to fail. Instead, it kept working. 1970s, engineering running 40 degrees below design temperature, still returning data. But time is running out. By around 2025 to 2027, there won't be enough power to run core systems and any science instruments. Engineers will have to start shutting down instruments permanently. By 2030, maybe 2032 at latest, the power budget will be exhausted. The spacecraft won't have enough power to communicate with Earth. Transmitters will fall silent. The Voyagers will continue to travel. They'll still be intact, solar panels and antennae and RTGs still attached, but dead. No power to run anything, no way to communicate, drifting silently through the void. And they'll keep drifting for an incomprehensibly long time. Voyager 1 is heading generally toward the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of the star, Gliese 445, closest approach to any star in Voyager 1's foreseeable future. 1.6 light-years is about 9.4 trillion miles. Voyager won't enter that star's planetary system if it has one. It will just drift past in the vast emptiness between stars. Voyager 2 is heading toward the constellation Pavo and Indus. In about 40,000 years, it will pass within 1.7 light-years of the star, Ross 248. After those close approaches, the Voyagers will continue wandering the galaxy. They might eventually pass close to other stars. Over millions of years, encounters with stars and their gravitational fields will gradually change the Voyager's trajectories. Over billions of years, the spacecraft will orbit the galactic center along with all the other stars, completing one orbit every 225 million years or so. The golden records will still be attached. Each Voyager carries a 12-inch gold-plated copper disc containing sounds and images from Earth. The record is designed to last for billions of years in the vacuum of space. Gold doesn't corrode or oxidize. There's no oxygen in space, no water, nothing to degrade the metal. Information is physically etched into the surface, not stored magnetically or electronically. Even if the spacecraft's electronics fail, even if power dies completely, the record will remain intact and readable, assuming you have the right equipment. The sounds on the record were carefully chosen to represent Earth's diversity. Natural sounds, wind, rain, thunder, surf breaking, volcanic eruptions. Songs of humpback whales recorded in the oceans, these haunting vocalizations that travel hundreds of miles underwater. Birdsong from multiple species, crickets chirping, frogs croaking, dogs barking, human sounds, a baby crying, that universal sound of new life, footsteps, walking, laughter, both male and female, a heartbeat, the rhythm that sustains human life. The sound of a kiss between mother and child. Tools being used, a hammer striking an anvil, metal on metal, a saw cutting wood, a tractor engine. Transportation sounds, a horse and cart, ancient transport, a train whistle, the industrial age, a jet aircraft, roaring, a Saturn V rocket launch, the very power that sent these spacecraft to space. Music from around the world and across history. Bach's Brandenburg Concerto No. 2, Beethoven's Fifth Symphony and String Quartet No. 13, Mozart's The Magic Flute, Stravinsky's The Rite of Spring. But the committee knew Western classical music couldn't represent everyone. Traditional music from Java with gamelan orchestras, music from Senegal with complex polyrhythms, pygmy music from Zaire, Aboriginal songs from Australia, some of the oldest continuous musical traditions on Earth, panpipe music from Peru, shakuhachi music from Japan, Chinese traditional music, Indian classical music, blues from the American South, jazz with Louis Armstrong's trumpet and vocals, rock and roll with Chuck Berry's guitar, Georgian choir music with dense polyphonic harmonies. The selection committee, led by Carl Sagan, struggled with difficult choices. Every piece represented thousands of alternatives that couldn't be included. How do you represent all of human culture on one disc? What defines us? What should we preserve? Greetings in 55 languages, from ancient Akkadian dead, for thousands of years, but representing humanity's ancient roots, to modern English, Mandarin, Chinese, Spanish, Hindi, Arabic, French, Russian. Each greeting is brief, peace, and friendship. Greetings from the children of planet Earth. We hope someday to join a community of galactic civilizations. This record represents our hope and determination and goodwill, similar sentiments in dozens of tongues. Then, there are the images, 116 pictures encoded on the record. Mathematical and physical definitions, diagrams showing numbers in binary, definitions of physical units, chemical structures, DNA structure, atomic structure. The solar system showing the sun and planets. Earth's position as the third planet. Earth seen from space, the blue marble. Landscapes showing diversity. Mountains, deserts, forests, oceans. Human anatomy. Reproduction showing how humans create the next generation. These images were controversial. Some thought them too explicit, others argued. Any intelligent species would need to understand biology. People of various cultures and ages, a family eating together, children playing, athletes running. Architecture from different civilizations. The Great Wall of China, the Taj Mahal, modern skyscrapers. Food art technology, a supermarket, a traffic jam, a page from Newton's Principia. The images were encoded as audio signals, technology familiar to anyone in 1977 who had seen slow-scan television. Lines scan across the image, brightness encoded as audio frequency. If found by extraterrestrials, they would need to figure out that certain audio encodes images. Clues are provided on the aluminum cover, showing pictograms explaining how to play the record. Rotation speed, 16 2/3 revolutions per minute. Position and configuration of the stylus. Diagrams showing how to decode images. Binary representations of timing parameters. A pulsar map showing Earth's location. 14 pulsars with unique periods like cosmic fingerprints. By showing periods and directions, the map locates Earth in space and time. Since pulsar periods slowly change, the specific periods indicate when the record was made. Creating the golden record was an enormous effort. Scientists, artists, musicians, linguists, anthropologists all contributed. John Lomberg created diagrams, Andrew selected sounds and music. Frank Drake designed the pulsar map. Linda Salzman-Sagan drew human figures. They had only months to complete it. The spacecraft were being built on tight schedule. Launch windows were inflexible. Technical constraints added to the challenge. The amount of data that could fit was limited. Audio quality had to be balanced against duration, image resolution against number of images. Every decision involved trade-offs. The golden record was more than science. It was philosophy, an attempt to answer profound questions. What does it mean to be human? What should we tell another intelligence about ourselves? What's worth preserving for eternity? What transcends our differences? Carl Sagan and his team knew the chance of the record being found was vanishingly small. The Voyagers are tiny in the vastness of space. The galaxy contains hundreds of billions of stars. The space between stars is incomprehensibly vast. The probability of passing close to another star system is essentially zero. Even if they did, the probability of a civilization existing there at the right time is even smaller. The golden record is more likely to be destroyed than discovered. In billions of years, the Voyagers might collide with something. They might fall into a star. They might be destroyed by radiation. But the act of creating the record was meaningful for us. It forced us to think about how we would explain ourselves. What's important? What's universal? What transcends culture and time? The golden record is a snapshot of Earth in 1977. Some languages are now extinct or endangered. Some music is no longer performed. Some images show things that no longer exist. But it's a time capsule, a message in a bottle thrown into the cosmic ocean, a declaration that we were here, that we existed, that we had thoughts and feelings and culture and dreams. If it's never found, that's okay. The value was in the creation, not the discovery. The value was in thinking about what matters, what endures. And now that record is in interstellar space. Attached to Voyager 1, traveling at 38,000 miles per hour. Through the medium, the spacecraft helped us discover, past the hydrogen wall, through interstellar clouds, carried on a vehicle built by a species that has existed for maybe 300,000 years, a mere eye blink on cosmic timescales. In 40,000 years, when Voyager 1 passes Gliese 445, will anything of human civilization remain? Will Earth still be habitable? Will we have spread to other stars? Will we have gone extinct? No one knows. But the golden record will still be there, still intact, still carrying its message. A testament to a moment when a young species looked up and dared to send part of itself outward. The Voyager program fundamentally changed our understanding of the solar system and its boundary. The cost was about $865 million total from start through Neptune encounter. In today's dollars, that's several billion, but spread over the decades of the mission, it's a remarkably small investment for the return. 4 planets explored in detail, dozens of moons discovered or studied, first observations of volcanism beyond Earth, first hints of subsurface oceans on icy moons, first measurements of the termination shock, first crossing of the heliopause, first direct sampling of the interstellar medium. Every textbook about the outer solar system uses images from Voyager. Every model of the heliosphere incorporates Voyager data. Every discussion of interstellar space references what the Voyagers found. The spacecraft rewrote our understanding of the solar system and its boundary. They showed that Io is geologically active, driven by tidal heating, a revolutionary finding that shattered assumptions about geological activity on small bodies. This discovery changed how we think about energy sources for geology. Not just radioactive decay in planetary interiors, but tidal heating from gravitational interactions can power volcanism and tectonics. This applies to Io, to Europa, to Saturn's moon Enceladus, and potentially to exomoons orbiting giant exoplanets in other star systems. They suggested Europa might have a subsurface ocean, hints from surface features that have driven decades of mission planning. Future missions to Europa are designed to search for signs of life in that ocean. If life exists there, it would prove life can arise independently in multiple locations, even in environments very different from Earth. They revealed the complexity of Saturn's rings, thousands of ringlets, shepherd moons, resonances, waves. The rings are a natural laboratory for studying orbital mechanics and disk dynamics. Principles learned from Saturn's rings apply to protoplanetary disks around young stars, to accretion disks around black holes, to galaxy disks. They explored Uranus and Neptune, the only spacecraft ever to visit those planets. Everything we know about their atmospheres, magnetic fields, and moons comes primarily from Voyager 2's brief flybys. Any future mission to these ice giants will build on Voyager's foundation. And then, after the planets, they continued into the heliosheath, across the termination shock, through the magnetic highway, across the heliopause, into interstellar space. They measured the distance to the heliopause and found it farther than predicted by 2.4 billion miles. They measured the shape of the heliosphere and found it asymmetric, compressed by the sun's motion through the galaxy. They discovered the heliosheath is filled with magnetic bubbles, a foam-like structure no one anticipated. They found the magnetic highway, an unexpected bridge connecting the heliosheath to interstellar space. They measured the properties of the interstellar medium and found them different from models: density, temperature, pressure, all slightly off. They confirmed the hydrogen wall exists, a superheated barrier beyond the heliopause that acts as an additional cosmic ray shield. They detected tsunami waves from solar storms propagating billions of miles through interstellar space. They measured the galactic magnetic field and found it oriented unexpectedly and varying over distances of about 100 AU. They mapped cosmic ray intensities and found anisotropies no one predicted, revealing structure in the local interstellar environment. Every one of these findings required scientists to update their understanding, to revise models, to reconsider assumptions. This is the value of exploration, not just to confirm what we think we know, but to discover what we don't know, to find the surprises, to learn that reality is more interesting than our theories. The Voyagers taught us humility in a profound way. We thought we understood the edge of the solar system. We built sophisticated computer models, ran simulations for years, made confident predictions. We wrote textbooks explaining the heliosphere, drew diagrams showing the heliopause as a neat spherical boundary, published papers calculating exact distances. And then 2 spacecraft actually went there and measured it. And we learned we were wrong about almost everything. Not fundamentally wrong about the physics, the basic picture was correct. Solar wind does meet interstellar medium. A boundary does form where their pressures balance. Cosmic rays are more intense beyond that boundary. But every specific prediction, every quantitative detail, turned out to be incorrect. This isn't a failure of science, it's how science works. We build models based on the best available data, We make predictions. We test those predictions. When reality doesn't match, we learn something new. We update our models. We refine our understanding. And then we make new predictions to be tested. The Voyagers exemplify this process perfectly. Scientists made honest predictions based on solid physics and the data available. Those predictions turned out to be wrong in important ways. Not because the scientists were incompetent or careless, but because the universe is more complex than any model can capture. There were factors scientists hadn't accounted for, properties of the interstellar medium they'd estimated incorrectly, dynamics of the boundary they hadn't anticipated. Phenomena like the magnetic highway, the hydrogen wall, the magnetic bubbles that no one had predicted could exist. And that's okay. That's how we learn. The wrong predictions weren't failures. They were opportunities to discover something new, to refine our understanding, to build better models. NASA is planning a follow-up mission called the Interstellar Probe. It's still in the concept stage, with no firm launch date or budget, but the science goals are clear. Answer the questions the Voyagers raised. The Interstellar Probe would be designed from the start for an interstellar mission. More power, longer lifespan, better instruments, faster velocity. The goal is to reach 500 to 1,000 AU within 50 years. 5 to 10 times farther than the Voyagers have traveled. To achieve this, the spacecraft would need to travel at roughly 80,000 to 160,000 miles per hour. About twice Voyager's speed or more. This requires either a more powerful launch system or a close solar flyby using solar thermal propulsion or some other advanced propulsion technology. The science goals include exploring the heliosphere's nose and tail in more detail. Voyager 1 crossed near the nose. Voyager 2 crossed toward the side. But what about the tail? How far does it extend? What's its structure? The Interstellar Probe would also explore the outer heliosphere more systematically. Voyager took point measurements along 2 trajectories. The Interstellar Probe could map larger regions, measuring how properties vary over distance and direction. And it would travel much farther into the interstellar medium. 500 to 1,000 AU is still incredibly close to the Sun on galactic scales, but it's far enough to see if the interstellar medium properties Voyager measured are typical or if they vary significantly over larger distances. The mission could also search for the heliopause bow shock if it exists. Models predict a bow shock in the interstellar medium, somewhere around 140 to 230 AU. But given how wrong models were about the heliopause itself, the bow shock could be anywhere or might not exist at all. The Interstellar Probe might find it or might not. Either result would be scientifically valuable. The spacecraft could carry advanced particle detectors to better characterize galactic cosmic rays, magnetometers to map the galactic magnetic field, plasma wave instruments to detect turbulence and waves in the interstellar medium, possibly even a camera to image the solar system from outside, taking a family portrait from interstellar space. But the mission is decades away. Design work is ongoing. Funding hasn't been secured. Even if everything goes perfectly, launch wouldn't happen until the 2030s at earliest, and the spacecraft wouldn't reach 500 AU until the 2080s. The scientists designing the mission probably won't live to see its primary results. This is the reality of interstellar exploration. The timescales are longer than human lifetimes. The Voyagers launched when many of the scientists analyzing their current data weren't even born. The engineers maintaining the deep space network weren't alive when the spacecraft were built. The people who will see the Voyager's last transmissions are likely in elementary school or younger today. Science on these timescales requires institutional commitment, continuity across generations, a willingness to start projects whose conclusions you won't live to see. But that's what exploration requires. Lewis and Clark explored the western United States, but settlement took generations. Magellan's expedition circumnavigated the globe, but he died before the voyage was complete. Apollo landed humans on the moon, but we haven't returned in over 50 years. Progress isn't linear, it's fits and starts. Periods of rapid advancement followed by consolidation or even retreat. The Voyagers represent a particular moment in history, a moment when funding was available, technology was adequate, planetary alignment was favorable, and institutional will existed to attempt something unprecedented. That moment might come again. The interstellar probe might launch humanity, might send more spacecraft into the interstellar medium, or it might not. The Voyagers might remain for decades or centuries, the only spacecraft to have directly sampled interstellar space. Either way, what they discovered stands. The data exists, the measurements are recorded, the surprises are documented. Future missions will build on what the Voyagers learned. But even if no follow-up mission ever happens, the Voyagers achieved something permanent. They showed us what's out there at the edge of the solar system in the space between stars. They showed us it's stranger, more complex, more dynamic than we thought. And they showed us we still have so much to learn. The spacecraft are dying now, slowly, inexorably. The plutonium in their RTGs decays, power output drops steadily, about 4 watts per year every year, without exception. Instruments are being shut down one by one to conserve energy heaters. Turned off, letting systems freeze backups, activated as primary systems fail. Engineers performing triage, deciding what to save and what to sacrifice. In 2020, NASA shut down the heater for Voyager 2's cosmic ray instrument. The instrument dropped to minus 74 degrees Fahrenheit. Engineers expected it to fail. Instead, it kept working. 1970s, engineering running 40 degrees below. Design temperature still returning data. This resilience, this robustness, is part of Voyager's legacy. The engineers who designed these spacecraft in the 1970s couldn't have known they would last nearly 50 years. But they built them with redundancy, with simplicity, with quality that has enabled decades of operation. Future spacecraft designers study Voyager's engineering to understand what worked, what lasted, what enabled this longevity. The lessons learned will inform future missions, not just to the outer solar system, but potentially to other stars. But time is running out for the Voyagers. By around 2025 to 2027, there won't be enough power to run core systems and any science instruments. Engineers will have to start shutting down instruments permanently. By 2030, maybe 2032, at latest, the power budget will be exhausted. The spacecraft won't have enough power to communicate with Earth. Transmitters will fall silent. The last signal will fade into the cosmic background noise. And the deep space network will no longer hear anything from that point in the sky. The moment when Voyager falls silent will be profound. For nearly 50 years, these spacecraft have been humanity's emissaries to the outer solar system and beyond. They've sent back data every day, images, measurements, discoveries that have transformed our understanding. When they fall silent, an era ends. No spacecraft currently under development will replace them in the outer heliosphere and interstellar space. The Voyagers are unique, irreplaceable. When they go silent, our direct connection to interstellar space ends until some future mission reaches those regions decades from now. But they'll keep traveling 38,000 miles per hour forever. Not slowing down because there's no friction in space. Not stopping because there's nothing to stop them. Just drifting outward, year after year, decade after decade, century after century, millennium after millennium. Moving through the interstellar space, they helped us discover through the medium they measured for the first time. Past shock waves from solar storms and stellar outbursts through varying densities and magnetic field structures. Past the hydrogen wall, eventually into regions we can only theorize about. All unobserved now, because their instruments will be dead. All unrecorded, because they can no longer communicate. But still happening, still real, still there. The spacecraft will become time capsules drifting through the galaxy, frozen in the configuration they had when power finally died. Instruments pointed in whatever direction they were last commanded. Antenna aimed at a star that's no longer our sun from their perspective. The golden records, still attached, still intact, still carrying their message. In 40,000 years, they'll make their closest approaches to other stars. Voyager 1, passing within 1.6 light-years of Gliese, 445. Voyager 2, passing within 1.7 light-years of Ross, 248. Still over a light-year away from anything not close enough to say they've reached another star system. Just passing by in the vast emptiness between stars. After those encounters, they'll continue wandering the galaxy. Over millions of years, encounters with stars and their gravitational fields will gradually change the Voyager's trajectories. They might pass closer to other stars, or they might drift into regions where stars are sparse. Over billions of years, the spacecraft will orbit the galactic center along with all the other stars, completing one orbit every 225 million years or so. The Sun will complete many more orbits. The solar system will change. The planets will migrate slightly. The Oort cloud will be perturbed by passing stars. But the Voyagers will keep drifting through the galaxy, carrying their message, carrying evidence that once, on a small planet orbiting an ordinary star, an intelligent species arose. And that species built machines that could travel between the stars. The golden records are designed to last for billions of years, but nothing lasts forever. Eventually, cosmic rays will damage the gold. Eventually, micrometeorites will erode the surface. Eventually, the information will degrade. Or the spacecraft might collide with something, a comet fragment, an asteroid, a planet, even falling into a star. The probability of any of these happening in the next few billion years is low, but over trillions of years, it approaches certainty. Eventually, the Voyagers will be destroyed, their atoms scattered, their messages lost. But for now, for the foreseeable cosmic future, they'll be out there. Humanity's first ambassadors to interstellar space. Proof that we existed. Proof that we explored. Proof that we dared to send part of ourselves into the unknown. The Voyagers represent something profound about human nature. Our curiosity, our desire to explore, our drive to understand. We're a species that looks up at the stars and wonders what's out there. We're a species that builds machines to answer those questions. We're a species that sends pieces of ourselves into the cosmos, not knowing if anyone will ever find them, but doing it anyway, because it matters to us. The pale blue dot image captures this beautifully. Carl Sagan, looking at Earth from billions of miles away, seeing it as a tiny speck, recognizing both how small we are and how precious our existence is. Everything we've ever known, everyone we've ever loved, every civilization that's ever existed, all of it on that tiny dot. And yet, we sent machines beyond that dot to explore the universe, to measure the galaxy, to discover what lies in the space between stars. That's remarkable. That speaks to something fundamental about who we are. The Voyagers have taught us scientific lessons about the heliosphere, about interstellar space, about magnetic fields and cosmic rays and plasma dynamics. But they've also taught us philosophical lessons about exploration, about discovery, about the value of venturing into the unknown, even when we don't know what we'll find. They've taught us humility, showing us that our best models are always incomplete, that reality is more complex than we imagine. They've taught us perseverance, showing us that machines built with care and quality can last far beyond their design lifetimes. They've taught us to think long-term, to start projects whose benefits won't be realized for decades, to build for future generations. These lessons extend beyond space exploration. They apply to how we approach challenges on Earth, how we think about our future as a species. The Voyagers are a testament to what humans can achieve when we work together toward ambitious goals. Thousands of people contributed to the Voyager: mission engineers, scientists, technicians, administrators. They built 2 spacecraft that have now operated for nearly 50 years. They analyzed data from the outer planets and the heliopause and interstellar space. They maintained the deep space network to communicate across billions of miles. They wrote software patches for computers built before most of them were born. They solved problems that no one anticipated when the mission began. This collaborative effort, across decades, across generations, is part of Voyager's legacy. It shows what's possible when people work together towards something bigger than themselves. And now, as the Voyagers approach the end of their operational lives, we can reflect on what they've meant. They've given us a new perspective on our place in the cosmos. They've shown us the outer solar system in exquisite detail. They've measured the boundary between solar and interstellar space. They've ventured into the galaxy beyond carrying a message from humanity. They've operated for nearly 50 years, far exceeding every expectation. And when they finally fall silent, they'll continue their journey through the cosmos. Silent, but still traveling, still carrying their message, still representing humanity's first steps into the interstellar medium. 2 spacecraft built with 1970s technology, computers with less memory than a calculator, transmitters weaker than a light bulb, power systems based on radioactive decay. Traveling for nearly 50 years, still teaching us, still surprising us, still showing us the universe is more interesting than we thought. Until the day they fall silent and drift into the eternal night, carrying their message to the stars. A message from a species that dared to explore, that dared to send a part of itself into the unknown, that dared to ask what lies beyond, and found answers stranger and more wonderful than anyone predicted.